The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Let's see, a couple of announcements. Tomorrow there'll be quiz 6 based on homework 6. Just on the crystallography, there's a little bit at the end of homework 6 on X-rays, and we will just start to talk about X-rays today. So I think that we'll leave that out. So just be based on crystallography. And I've asked the recitation instructors to administer the test at the end of the period so you can have some chance to ask questions. Last day we talked about crystallography. We were introduced to the 7 crystal systems and the 14 Bravais lattices, which are shown up on the slide taken from the lecture notes. And we saw that if we wanted to describe the arrangement of atoms in a crystal, we could do so by combining the notion of the Bravais lattice, of which there are 14 distinct types, with a basis. The basis could be a single atom, could be a group of atoms, could be an ion pair, could be atom pair. And we saw that got us through an elaborate set of crystals. And then towards the end we focused on cubic crystals, because cubic crystals are representative of a large number of metals in the periodic table, and it's much more tractable mathematically. So we're going to focus on cubic crystals, and I'm going to continue along with that today. And in particular I want to start looking at notation. And the reason I want to look at notation is I want to be able to define a point, a line, and a plane, so that when we start characterizing crystals, I can give you a mathematical notation that represents the face of the cube, the body diagonal of the cube, a line going on the body diagonal, a line going along the edge. Instead of writing it in words, I want to be able to do so mathematically. And so for that, we're going to turn to this handout, which has the elements of crystallographic notation. I'm going to quickly go through this. I think last day we started talking about position. So I've drawn a little sketch here. This is the unit cell. The unit cell is the cube, because we're talking about a cubic system. And this is just the lattice. I haven't put atoms here. Okay, so I'm just talking about lattice points in space. And just to remind us, A, B, and C are the unit vectors. And in a cubic system, A equals B equals C. And each of them is equal to A, the lattice constant. This is the lattice constant, A. Well, that's the dimension A, the lattice constant. And all angles are right angles. So alpha equals beta equals gamma equals 90 degrees. So just to practice, the origin, as I've shown here, the origin, all we do is write 0, 0, 0, as you would in your math class, but don't put parentheses around it, because parentheses are reserved for planes. We're going to use parentheses later on. The crystallographers have their own notation. Okay, so here's point A. Here's point A. What do we see? It's out. It's in the YZ plane. By the way, I've chosen a set of coordinate axes that are in conformity with the right-hand rule. I don't care which axis you choose to be X. It doesn't matter. I generally like to make Z vertical, but I don't care as long as you use the right-hand rule. You need to observe the right-hand rule, because in physics you're going to find that there are certain vector forces that are the product, cross product, and if you don't use the right-hand rule convention, you'll get things identically backwards. So the thumb is your x-axis, y-axis, z-axis, however you want to do it. So I've got the x-axis coming out of the board, the y-axis and the z-axis are in the plane of the board. So if we come here, this point A is 0 units out on the x-axis, it's 1 unit out on the y-axis, 1 unit up on the z-axis, so this would be 0, 1, 1. And B, as I've drawn it, looks like it's 1 unit out on the x-axis. It's no units out on the y-axis and a half a unit up on the z-axis. So that's 1, 0, a half. So that's about the last time I'm going to talk about these things. It's more interesting to talk about lines. So for lines, I'm going to say, let's just follow along the slide. And the slide imitates what's going on here. So let's see, I've got a couple of them I want to try. Let's look at, for starters, OB. We want to look at OB. So I'm going to start at the origin, and I'm going to come out to the point B, and I've got a vector on this. It's emanating from the origin out to B. And what does it say to do? It says, define a vector from origin to the point on the line, choose the smallest set of integers, etc. No commas. So I put the origin, which conveniently here is the origin, out to the point along that direction. So the vector OB as written will go from there out to, what is it? Goes to 1, 0, a half. But then it says, let's see, no commas, enclose in brackets, and clear the fractions. They don't like to have fractions when you're talking about lines. So clear the fractions, multiply through, so then that'll just double it, 2, 0, 1. And you could say, well, what are they doing? Actually, if you can imagine going out one more unit cell, this line would actually go through the point 2, 0, 1. So you're just looking at the projection along here. You're just multiplying it. And then it says no commas and enclose in brackets. Okay, this is called a bracket. These staple-like things are called brackets. So that's a direction, the direction OB. Let's do the, let's see, what's the other one we're going to do? What is it? AO? AO. All right, so it says you have to move the origin to the base of the vector. So if I want to do AO, I have to put the origin up here at the tail of the vector. So if this is the origin, I'm moving actually what? I'm not moving anywhere in the x-axis, but I'm moving -1 in the y-axis and -1 in the z-axis in order to get this direction. So I'm really going 0 in the x, I'm going -1 in the y, and -1 in the z. And you can see, since we don't use commas, putting minus signs would look cumbersome. So in crystallographic notation, the minus sign is represented as a macron. A macron is a line over. So this is 0, 1 bar, 1 bar. That's equal to -1. But in crystallographers use the term 1 bar. So this is O, 1 bar for this line, A down to origin. So that's how that's done. And then it says, let's see, we can denote an entire family of directions by carets. So let's do that. If I want to, suppose I wanted to say, what have I got up there? All of the body diagonals. Well, how would I get a body diagonal? A body diagonal, if this is the origin, and I want to go up the body diagonal, it would be out 1 unit, out 1 unit, out 1 unit. So it would be 1, 1, 1 would be a body diagonal. Right? But suppose I want to say all body diagonals. That's 1, 1, 1 this direction, 1, 1, 1 that direction. I want to get this body diagonal. I want to get that body diagonal. How do I do that? I can do that by putting carets. These are called carets. Those of you who have done some editing and proofreading know these terms. Okay? So carets. So this is all body diagonals. This is all body diagonals. We could do a few others while we're at it. Suppose I wanted to do all of the face diagonals. All of the face diagonals, like this, and then over here, like this, like this. Well, what's a face diagonal? 0, 1, 0, 1, 1, right? So all the face diagonals would be, okay, all face diagonals. What about all cube edges? What's a cube edge? Cube edge could be this one. 0, 0, 1. So this would be all cube edges. So what does it mean? It means write this out in full. So that's 001, okay, 001 bar, 010. See, I'm using O for 0. I'm cluing you into crystallographers' talk. That's how they talk, O and 1 bar. So you're going to be really hip if you end up in an elevator with a bunch of crystallographers, okay? And there's 2 others here, 100 and 1 bar 00. Well, how many faces are there? 6. How many face edges? 6. And look, just going through the permutations and combinations gives you exactly the number that you should have. This is mathematics imitating reality. That's good. That's good. And likewise here, if you go through all the permutation combinations of 0, 1, and 1 bar, you'll end up with all of the possibilities for face diagonals, all the possibility for body diagonals. I think I've got a cartoon here that shows, there it is. It shows all of the different diagonals that are possible when you mix 1 and 1 bar. Okay, that's good. So that's so far so good. That's pretty simple. Now let's look at planes. Let's look at planes. For planes, we use something called the Miller indices. Miller indices for describing planes. And they're named after the British mineralogist William Hallowes Miller, who back in the 1830s gave us this means of describing a plane. And I think it was, rather than write it down, we'll just follow along here because you've got the notes in front of you. You know from your math that the equation of a plane is x over a plus y over b plus z over c equals 1. And a, b, and c are the intercepts with the x, y, and z axes, respectively. So what Miller did is he said, let's let h be 1 over a, k be 1 over b, and L equals 1 over c. So this becomes the equation of the plane. hx plus ky plus lz equals 1. And now what you do is you take the h, k, and L and enclose those in parentheses. So in other words, he's taking the plane index to be the reciprocals of the intercepts with the 3 axes. And you'll see why in a second. You'll see why in a second. Why do it that way? Well, because every once in a while something like this happens. So here's a simple one just to get our feet wet. So here A, B, and C are the unit vectors. So this is the x-axis in the same convention I've chosen. X is coming out of the plane of the slide. Y is moving to the right. And Z is moving up. Okay? So here's a plane that's shaded in. And what do you see? It cuts the x-axis at x equals plus a half. It cuts the y-axis at y equals plus 1. And it never cuts the z-axis. It's parallel to the z-axis. So mathematically, we would say the z-intercept is infinity. And who wants to have infinity? So now you see the wisdom of Miller. Miller said, let's describe this in terms of the reciprocals. So what's the reciprocal of a half? It's 2. What's the reciprocal of 1? It's 1. And what's the reciprocal of infinity? 0. So we can describe this plane as the 2, 1, 0 plane. Whenever you see a 0, whatever place the 0 lies, that means that plane is parallel to that axis. So right away I can say that's a plane that's parallel to the z-axis. It doesn't cross the z-axis. So there it is. So there's the formula. You take the reciprocal of the intercepts, put them side by side, no commas, and this is why we save the parentheses. And that's why we don't put our position in parentheses, because we're saving parentheses for the plane. Oh, let's do a few more. This is, wow, it's a lot of fun on a Monday. See, you're excited to be back in class. And man, there's a cool thing that happens when you use Miller indices. You see what I just did? I just drew a direction. And that direction is the 2, 1, 0 direction. And what do you notice about the position of 2, 1, 0 versus the 2, 1, 0 plane? When you write directions according to this formula and planes according to Miller indices, the 2, 1, 0 direction is perpendicular to the 2, 1, 0 plane. 2, 1, 0 direction is perpendicular to the 2, 1, 0 plane. Let's do another one. Oh, this is a good one. This is a plane that cuts the y-axis at y equals 1. It's parallel to the x-axis, parallel to the z-axis. Never cuts the x or the z-axes. So that's an 0, 1, 0 plane. I mean, you can do that in your head, right? So that's an 0, 1, 0 plane. That's an 0, 1, 0 plane, and so on and so forth. Here's an 0, 2, 0 plane. Why? Well, because it cuts the y-axis at y equals a half. We take the reciprocal is 2, so 0, 2, 0. 0, 2, 0. And let's try again. Well, there's 0, 1, 0 direction, and what do you know? The 0, 1, 0 direction is normal to the 0, 1, 0 plane. And 0, 2, 0 direction is normal to the 0, 2, 0 plane. What do you know about the 0, 1, 0 direction, the 0, 2, 0 direction? They're the same direction. Anything O is going to be along the y-axis. Now that's an 0, 2, 0 plane. I could shift the origin to here, couldn't I? So then that would be an 0, 2, 0 plane, and that would be an 0, 2, 0 plane. Well, here's some more. 1, 1, 1. Well, look at this plane here. It cuts the x-axis at x equals 1, the y-axis at y equals 1, the z-axis at z equals 1. So shade that in. That's the 1, 1, 1 plane, but that's also a 1, 1, 1 plane. We can keep shifting the origin. I don't know where the origin of the universe is, so I can move this anywhere along. Here's one. Here's backwards. See, this now is 1, 1, 1 bar, because if I put the origin here, I'm cutting the x-axis at +1. I'm cutting the y-axis at +1, but I've got a negative tilt to this plane, so the z-axis is being cut at -1. So again, we try to use the minus sign, avoid the minus sign rather, and instead we put the macron over the number, and in that way we give the minus indication on a number. No commas in parentheses. Now let's do the test. Here's the 1, 1, 1 direction, and sure enough, the 1, 1, 1 direction cuts the 1, 1, 1 plane normally. Let's try over here. There's the 1, 1, 1 bar direction. Boom, cuts through the 1, 1, 1 bar plane normally. It's fantastic. Fantastic. And we can do families. We can do families of planes as well. So let's look at families of planes. What kind of families could we could come up with if we want to do families of planes with brace brackets, right? Families of planes use braces. So if I want to say all cube faces, that would be 001. Because 010 we saw was parallel to it cuts the y-axis, parallel to the xz plane. So that's going to tell you to roll over 0, 0, 1, and 1 bar in this manner, only instead of brackets you've got braces. How many faces on a cube? There's 6. How many combinations of 0, 1, and 1 bar are there? 6. So there you go. And by the way, one other thing, if you want to be hip with the crystallographers, this is one way of writing it. Another way of writing it is 100. 100 is equivalent to 001, but crystallographers like to put things in ascending order. So the crystallographer would never write 100. Crystallographer write 001. So that's a cool factor there. If you want to get, you never know when you're going to meet a crystallographer on an elevator. It could come in. Yeah, it could be the icebreaker because they might be shy. Okay, and the last thing I want to do is talk about the distance calculation. Another virtue of using Miller indices. I want to put this up here because it's on the handout, but I want to make sure that it gets on the board. The HKL plane is perpendicular to the HKL direction when we use such a notation. And then I want to show, let's go back to the previous slide. Go back 2 of them because it's easier to see here. I want to calculate the distance between adjacent planes of the same index. So we can calculate the distance between adjacent planes of the same index. So what's the distance between 2 adjacent planes of some value HKL? And that's given by the following formula, which again is a testimony to Miller. The distance, and I'm going to subscript it HKL because they're all the same index, is given by A, which is the lattice constant, divided by the square root of h squared plus k squared plus L squared, where A is the lattice constant. Okay? So let's test it. If HKL is 010, well, trivially, that separation should be A, the lattice constant, and I think you can see that quite nicely up on the screen here. It's one lattice constant between successive 010 planes. Let's try it with 020. Well, it's going to be the square root of 2 squared, which is A over 2, and sure enough, what's the distance between 020 and the adjacent plane comparable to it? It's only half a lattice constant. So in essence, if you look here, every 020 plane is only half a lattice constant away. Every 010 plane is full lattice constant. So what you're really seeing then is that the distance, d goes down, the distance between planes goes down as the Miller index goes up. And what's the lowest Miller index? The lowest Miller index is 001. Lowest Miller index is 001, so that's a lattice constant. That's the maximum separation. And I think you can see that as you move HKL to higher values, what you're doing is you're cutting at a higher angular slice. And as you cut for a higher angular slice, the distance between successive planes is going to be reduced. Mathematically, what's going on, this is getting larger in the denominator, this is remaining the same, so that distance becomes closer and closer together. And why am I showing you this? Because we're going to use it in the very next unit. Not 3 years from now. We're going to use it in the next unit when we take this information and characterize crystals. And we're going to characterize atomic structure by the use of something that is comparable in dimension, right? If we're going to measure the dimension of the human hair, we're not going to use a yardstick. What kind of numbers are we looking at for these distances? We're looking at something down around some number of angstroms. So we better find some tool that gives me units of some number of angstroms. And that tool will be X-rays. X-rays. So now let's look at characterization. Characterization of atomic structure by X-rays. So today I want to talk about the discovery of X-rays and the underlying physics, and the next day we're going to look at applications. So first of all, what are X-rays? X-rays are a form of electromagnetic radiation. They're a form of electromagnetic radiation. Electromagnetic radiation. So what's that mean? That means all of these formulas apply. E equals h nu equals hc over lambda equals hc nu bar. That applies. That applies. And the special characteristic of X-rays is lambda is very short, and typically there's no hard rule on this, but just in round numbers, we're looking at between 1/100th to 100 angstroms. It's centered at about 1 angstrom, where 1 angstrom is equal to 10 to the minus 10 meters. I know it's not an SI unit, and you know my aversion to the nanometer, but I'll put it up here because I'm required by the International Union of Pure and Applied Chemistry and the Système International to put this contemptible unit here, but I love the angstrom. So this is just my personal preference. Okay, so let's plug in a value. Suppose we have 1 angstrom as the wavelength. If I use hc over lambda, where lambda equals 1 angstrom, or 10 to the minus 10 meters, I end up with 12,400 electron volts per photon. Per photon. 12,400 electron volts per photon. And this is clearly going to be powerful radiation. Let's take a look here. I pulled this out of the back of the text. This has ionization energies for the first 7 elements. So if you look here, this is in green I'm showing the first ionization energy, and this is right off your periodic table, right? 13.6 electron volts. I've rounded it to 2 significant figures. So it's 13.6 for hydrogen, it's 25 for helium, it's 5 for lithium, and so on. So these are tiny, tiny numbers. These are electron volts. All right? Now what we can do is look down this row. This is the last electron to come off. Okay? So the second ionization energy of helium is for a 1 electron atom, right? Helium has 2 electrons. If it loses 1, it only has 1 left. So this is a 1 electron atom. This is a 1 electron atom. This is a 1 electron atom. And look at the energies. This is for the innermost electron. Well, a 1 electron atom, that'll conform to the Bohr model. And sure enough, look at the ratios of these numbers. These are determined by X-ray photoelectron spectroscopy, and roughly 14 times 4 is 56. So there it is, 1 to 4 to 9 to 16. And it's just a manifestation of what you've seen as the ground state energy in the Bohr model goes as the square of the atomic number. So everything's making sense. But what I draw your attention to is, look, this is the innermost held electron of nitrogen. It's 668 electron volts, and I've got 12,400. This has enormous power. This has the power to ionize inner shell electrons. This is like a bowling alley. This is like a bowling alley, and all the pins are going flying here. This is incredible energy. So, what's the underlying principles here? Well, I think we have to start with a history lesson. So we'll start with a history lesson. We'll go back to November 8th, 1895. It was a dark and stormy night. Really, it was a dark and stormy night on November 8th, 1895 in Würzburg in Bavaria, which is now part of Germany. And there was a physics professor there by the name of Wilhelm Röntgen. Wilhelm Röntgen. And he was doing research, as many people were at that time, on gas discharge tubes. We've seen gas discharge tubes a number of times in 3091, and Röntgen was part of that army of researchers. And what Röntgen's specialty was, he was pursuing gas discharge spectral analysis under reduced pressure. So he was pumping down with a vacuum pump to get the gas pressure very, very low and very, very high voltage. That's what his take was. He wanted to look at high voltage and very, very low pressure. And let's take a look at what his apparatus looked like. Well, we'll start with the tube. As you've seen many times, we'll put the cathode to the left. We'll put the anode to the right. And he had the laboratory on the second floor. Laboratory on the second floor. His apartment was on the first floor. And down in the basement, he had a bunch of batteries, chromic acid. Chromic acid in open beakers down in the basement. So let's indicate that with the classical symbol. And this altogether put out about 20 volts. And then what he did is, he was a professor of physics who understood some electrical engineering. So he had a choke coil here. So the choke coil would take the current, store up, and 8 times a second, it would discharge. And it would discharge at 35,000 volts. So he could take 20 volts and up it to 35,000 by the use of this choke coil. So 8 times a second, he had 35,000 volts coming off the cathode here. So you've got bam, 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 but speed that up about 8 times, and that's what's going on. And so with 35,000 volts, he launches electrons off the cathode, and they go zooming across what is very, very low pressure gas and crash into the anode. And in the meantime, to keep this thing dynamically at low pressure, this goes to a vacuum pump. Vacuum pump to keep this thing pumped down as low as he can. And he was measuring what was going on inside this gas tube. And so he had a detector. And his detector was over here. The detector was off to the side. And the detector consisted of either a piece of cloth or a paper towel, which had been painted with a chemical that would glow when it was struck by something. What would the something be? Something would be electrons or photons that have an energy high enough to cause excitation of something in the paint and then re-emission in the visible. It doesn't do any good to excite electrons in the detector to have them re-emit outside the visible. Okay, so that's what's going on. So this was paper or cloth, and it was painted with an aqueous solution of barium platinocyanide. Yummy stuff. Barium platinocyanide, which glows green. It glows green when it's excited. And this is called a scintillation screen. Scintillation screen. Comes from the Latin word for spark. Scintilla means spark in Latin. So when the screen is struck by some form of energy, it will glow. And so he'd had dinner, and he was up on the second floor cranking away after dinner. and it was dark, it was raining. He had the windows open, and a street light was coming in. Oh, by the way, Röntgen suffered from daltonism. He was red-green colorblind, and this was a green screen. And with 35,000 volts, even at reduced pressure, given the capacity of those days for vacuum pumps, he still had a lot of glow from the tube. So the tube is glowing. He's got a street light in the background, so he decides to close the drapes and take out the street light. And then furthermore, he decides to darken the room, so he puts a cardboard box over the tube. So now the tube is enclosed in a cardboard box, so it's not glowing visibly to him. It's glowing inside the box, and he continues to see scintillation, continues to see things glowing. So he says, that's something interesting. The other thing that happened was kind of interesting. His graduate student who had prepared some of the apparatus, I guess he was practicing painting the scintillation screen. So what the student had done was to paint the letter A on a paper towel. And he left the paper towel on the lab bench. So now Röntgen's got the tube enclosed in cardboard. This thing's glowing. He looks down, he sees the letter A. The letter A is glowing. And he's going, wait a minute, this is crazy. So he says, all right. So he takes a piece of black paper and he puts it here in between the tube and the screen continues to glow. And then he says, he had a deck of playing cards in his lab. So don't laugh, that's how Mendeleev discovered periodicity. So he takes a playing card, he puts the playing card in front, and the tube continues to glow. And then he takes a book, and he puts a book in between, and the tube continues to glow. So he's getting, wait a minute. So then he grabs a piece of lead foil, and he puts the lead foil in here, and what happens is that where the lead foil is, the screen is not glowing, but then he sees the outline of the bones of his hand on the lead, holding the lead foil. So all of this stuff is going on, and he just goes to town. He says, you know what, this can't be electrons, because electrons can't live in air. They'll be stopped by air. So he knew about radio waves from Hertz, and he said, could this be some form of mysterious radiation that's capable, and he was really afraid to say this, a form of radiation that's capable of penetrating matter. It's 1895, and you're going to come out publicly and say, I have a form of radiation that can penetrate matter. So he gets a magnet out. He moves a magnet. It doesn't change. So the stuff isn't sensitive to a magnetic field, but if he puts a magnet here, of course, he gets changes. He can't see this stuff. He can only see evidence of it. It's mysterious. It's mysterious. So he calls it X, the unknown quantity. It's X radiation. X radiation. This is November 8th, 1895. And to show you what a great scientist he was, rather than rushing to publication, he spends all of November and December repeating the experiment and trying it in different ways until he's convinced that the effect is real. And then around Christmas time of 1895, he sends off a manuscript, and it's published in the first week of January of 1896, and it takes the world by storm. He's announcing that there's a form of radiation that can penetrate matter. And furthermore, he's got an X-ray of a human hand. You know, this is the 1890s, so people are, you know, very prude, very private. He's got a form of radiation that can look inside the human body. This is really shocking stuff. So already on January 16th, 1896, there's an article in the New York Times. About this stuff. Mysterious form of radiation. Oh, by the way, you know, he was doing his experiments. How was he recording his results? He was recording his results on photographic film. And his photographic film was fogging. He had his photographic film stored in a cabinet on the other side of the lab. And half of the time he'd take the photographic film out and it was fogged. So whatever this stuff is, it's penetrating everything. It's penetrating the drawers of his file cabinet. They weren't steel cased. They were probably wooden file cabinets, right? So widespread adoption. Widespread adoption. Some of it silly. What's some of the silly ones? In London, there was a manufacturer announced, remember this is prudish Victorian England, that he could sell you X-ray proof ladies' underwear. In France, there was no such thing. The French don't care about such matters. So instead, this was, remember, the French, Daguerre had invented halide photography. So someone in France offered to X-ray the human soul. This is very good. I'm ashamed to say what happened in the United States. The New York City College of Physicians and Surgeons announced that they would use X-rays to project anatomical diagrams from textbooks onto the brains of medical students, thereby creating, and I quote, an enduring impression. In Iowa, somebody offered to X-ray copper pennies and thereby turn them into gold. So that's what happened. But seriously, what really did happen very quickly was the use of X-rays as a diagnostic tool. Already in February of 1896, there was a Scottish physician who used X-rays. And look, it's simple. It's just that you could do this in a high school. I mean, what is it? You know, it's just a gas discharge tube, pair of electrodes with a feed through, and, you know, he's got 35,000 volts. I mean, that's kind of stuff that comes off the chassis of your television set. And this is trivial stuff. You know? So people are putting these things everywhere. They're sitting in offices in open view. Nobody knew. So this physician had a seamstress come to him. She was involved in an industrial accident in a mill. A needle broke off in her hand. Now, how would you find the needle in a hand? You can't. Well, X-ray, they identified the location of the needle, performed the surgery, boom. For dental applications, it was immediately adopted. They were already using it in 1899 as a form of treatment for cancer. Very interesting. Took over. So what's the relative physics? What's going on here? So where do we have to go? I say we have to look at the anode, because that's where the electrons are crashing into. That's the site of the collision, isn't it? Something's happening at that anode. So let's look inside the anode, and suppose it's copper. What could we say about it? The anode. This is where the electron collision, that's the maximum impact, isn't it? So let's just see what might be going on. I want to show you the power of estimation. Okay? How far down? I've shown you that with nitrogen at 668 electron volts to get to the inner shell electrons. What about in the case of the anode? Well, what's going on there? Well, I can say, what's the energy of the 1s electron in copper 28 plus? That's a 1-electron system. Okay? And you know that in real copper, with all of its electrons, this value is going to be an overestimate, because the presence of all the other electrons is going to sap some of the protonic Coulombic force. So this will be an upper bound of what that energy could be. We know that's simply equal to the energy of the 1s in hydrogen, right, times Z squared. So if I take 13.6 electron volts times 29 squared, I get 11.4 thousand electron volts, which is still less than the 35,000 electron volts that Röntgen had. So Röntgen is running a huge bowling alley here. He's able to knock out 1s electrons from copper. And what happens when you knock out electrons, inner shell electrons? What's the next thing that happens? Well, let's look at an energy level diagram. So let's suppose this is the anode. So this is the anode in the gas tube. This energy level diagram. So this is going to be n equals infinity. And we'll just do a few of them. So this is n equals 4, n equals 3, n equals 2, and n equals 1. Not to scale. I'm trying to show that they're a little bit farther apart as you go lower and lower. And so this is ground state energy, E1. This is n equals 2 shell, n equals 3 shell, n equals 4 shell, and out here it's 0, isn't it? And so what do I have? I've got some incident electron that comes zooming in here. Zooming in here. This is incident. This is the one that's been accelerated, right? So the energy of this electron, it's all kinetic, and that's equal to the product of the charge on the electron, which is elemental E, times the plate voltage, which is 35,000 volts. That's how I get 35,000 electron volts as the energy. And it can come in, and we've just shown that it's got enough energy that it can even knock out an inner shell electron. It can even dislodge an inner shell electron. So let's see what would happen if that were the case. It dislodges an inner shell electron. What's the next thing? Well, I've got a vacancy down here. So what will happen? Well, an electron will fall from n equals 2 to n equals 1. And when it does so, it gives off radiation. It gives off radiation. Well, if it falls from n equals 2 to n equals 1, there's a slim chance it might even fall from n equals 3 to n equals 1, or maybe even n equals 4 to n equals 1. Well, heck, if it can go from 2 to 1, there's a vacancy in 2, so I might get 3 to 2, I might get 4 to 2, and you get the picture. You get a whole cascade here. You get a whole cascade. Each one of these gives off photons, photon emission. So you have expulsion of K shell, all of the electrons, but you can go all the way down to the K shell electrons, and then cascade and accompanied by photoemission. Photoemission. The difference is that instead of being in the visible or the infrared, these energy levels are so tightly bounded that this is in the X region of the spectrum. This is in the X region of the spectrum. And we have labels for these different photons. And first of all, you know, the spectroscopists don't like the numbers. This is the chemist notation. N equals 1, N equals 2, N equals 3, N equals 4. The spectroscopists call the ground state K shell. This is M shell. This is N shell. Okay, I left out a letter in the alphabet. K, L shell, M shell, N shell. So we can label this as a photon that came from a cascade down to the K shell. And to distinguish this K shell electron from the K shell electron involving a transition from n equals 3 down to n equals 1, we have a second indicator, and that's the subscript alpha. So this means the cascade down to K shell, and the alpha represents how far the electron traveled, okay, from one shell away. So that means from n equals 2 to n equals 1. This is a K beta photon. This is a K gamma photon. So this is like a Lyman series. All right? This is like a Balmer series because it always ends at n equals 2. N equals 3 to n equals 2 gives us a photon, and that photon is going to be called L alpha. N equals 4 to n equals 2 will give us a photon, and that's going to be called L beta. So I'm going to get a whole spectrum. I'm going to get a whole spectrum. Let's take a look at what that spectrum might look like. I could calculate any one of these. I could say lambda of copper K alpha would equal what? It's the same as you've seen before, Hc over what? The energy of n equals 2 shell to energy of n equals 1 shell. So what can we do? We can measure this. We know H and C. We can calculate what those energy levels are. All right? So let's plot this out. I could make a plot of wavelength, intensity, and I will get an entire spectrum of lines. I'll have first this is high wavelength, so that means energy is increasing from right to left. So the highest energy is over here. So what's the highest energy up there? The highest energy looks like n equals 4 down to n equals 1. So that's going to be over here. So this could be K gamma, then K beta, K alpha, and then the L lines are 3 to 2, 4 to 2, so they're over here. So this is L alpha, L beta, and so on. And these different wavelengths are associated with different energies. And these different energies are associated with what? They're associated with the binding inside the atom, inside the target. So every target has its own number of protons, its own number of electrons. So this set of lines is characteristic of the target. It's characteristic of the target. And I had to do a whole year of X-ray crystallography as a junior back at the University of Toronto. We used copper as the target. I will know on my deathbed that the wavelength of copper K alpha is 1.5418 angstroms. Okay? So if I walk into the room and I see 1.5418 angstroms, that's copper. It comes from copper. And any other element is going to give me a different set of lines. So what I'm learning here is I have a way of identifying elements. So this is now turning into something that could be a technique of chemical analysis, and we'll return next day to see what else we can do with it. Just for the last 5 minutes, I'm going to show you a little bit more about Röntgen and his discovery, but I wanted to draw attention to our winner from Friday who was unable to attend the lecture, and so I want to ask Nevera Gabriel to stand and accept her acknowledgement for the fine job she did on the actinide thing. And she's wearing her scarf. Why don't you come down and people can see you wearing the really super hot American Chemical Society scarf. Thank you. Good. Good. Now, here's the dark and stormy night the following morning. It's sunny. This is Röntgen's laboratory on the second floor of his flat in Würzburg. It's a museum today, and you can see the tubes and the lead wires going down to the basement and so on. Now, hold it. I don't want a lot of noise. No, just... All right, this is the first radiograph ever. This is Röntgen's wife, Bertha. Yes. You know, he noticed that there was a shadow with the lead, but Röntgen, I mean, he was smart. I mean, he had to share the glory, so he said, honey, would you mind coming upstairs? I'd like to take your picture. And so Bertha put her hand in the path of the X-ray, and for 15 full minutes waited while those X-rays went through. You can see the ring on her finger and so on. She endured in that 15 minutes greater than a lifetime dose of what we would consider safe today. People just didn't know. Anyways, this gave birth to medical radiography. And I would, just out of curiosity, like to know, is there anybody in this room who's never had a medical or dental X-ray? I see very few. I see a few hands. Few hands. To you I say congratulations, and I hope you keep up the good work. Okay, here's a second thing. So we have radiography that came out of Röntgen's discovery. Röntgen had a beam torsion balance. Okay, you know, like the Justice, she's got the two scales. So on one scale you put the unknown, and the other scale you put the calibrated mass. So he had a set of brass weights here in a wooden box. And he closed the wooden box, and he irradiated the box with the X-rays and took this photograph. And what do you see? You see that different materials have different electron densities, and therefore the wood is transparent more or less to X-rays, whereas the brass is less so. So you have a differentiation. You know, the way we see things is by differentiation. So here you have a differentiation. So he could identify what was in the box when the box was closed. So that gives rise to security technology. Every time you go to the airport, you are subjected to this, and it started with Röntgen. Röntgen also had a gun. It was a musket. Come on, he wasn't holding up convenience stores. What are you laughing at? You know, he had a gun, right? He went hunting. So he took an X radiograph of his gun. And this is used today, it gives birth to the technology of failure analysis. In fact, there are certain types of weld, typically involving very dangerous circumstances, such as pressure vessels that are going to contain steam at very, very high pressures. The code is that every inch of the welded seam must be inspected by X radiation in order to find what? Internal cracks. Because if there's a crack, there's a difference in electron density, and so you'll see contrast in the X-ray photograph. So from that experiment come three technologies. And for his work, Röntgen was the recipient of the very first Nobel Prize in Physics. It was awarded in 1901, and he was the unanimous choice of the world physics community for what he had done. And you're going to see next day more that the discovery of X-rays enabled. But one last thing. What a fine human being he was. You know what he did with his winnings? He donated them to the University of Würzburg to be made an endowment for student scholarships. And to this day, physics students at the University of Würzburg are recipients of scholarships that were endowed by Röntgen with his Nobel Prize winnings in 1901. I'll see you on Wednesday.